All right, so we're looking at, this is 10.3, the first video for 10.3, and we're going to talk about polar coordinates in this section. In this video, we'll introduce some of the basic ideas of polar coordinates, some of the properties, things like that. It's not going to be too long a video, or it shouldn't be. And then in the day 2, we'll get into some of the calculus of using calculus with polar coordinates. All right, now one way to give someone directions is to tell them to go 3 blocks east and 5 blocks south. That's more along the rectilinear or the normal Cartesian directions. Another way to give directions is to point and say go a half mile in that direction. That's more along the lines of polar coordinate system. So that's kind of the easiest way to think about it. With the Cartesian plane, we're dividing everything into x, y, and if it's 3 dimensions, z. Whereas with polar, we're talking about a direction and a distance. That's it. So each point that we have, and we're talking about each point. Now we've talked about vectors, that's one thing. And polar graphing is very much related to vectors in that you're going to have a direction and you're going to have a distance, where we talked about it being a magnitude before. Now it's just a distance from the origin. So when we do a polar coordinate system, the polar coordinate system where the Cartesian plane was divided by x and y axes, with the polar we're only going to have one, and that's just going to be the initial ray. We're going to have the origin, and we're going to have one ray that goes off in what we would usually call the positive x direction, but there is no x and y in the polar system. So from this initial ray, we're going to measure our angle and our distance that we are going to call radius, because that's what it is, because this is kind of based on a circle thing, and that's where how we're going to define this point. So this point, let's say this is 5, and this is a angle of, let's say, pi over 4. We would actually define this point as 5 comma pi over 4. That would be how we would do the coordinate pair in polar system. So the radius and then the angle, theta. So that's how we would define this one point right here. It's not this whole drawing, it's just that point. 5 pi over 4 is the coordinate plane, coordinate definition of what that point right there occupies. All right, now some curves are easier to describe with polar coordinates as opposed to the Cartesian or the rectangular coordinate system we're used to. R equals A is just a circle that's centered at the origin, because R is just going to be some number, and that's going to be the radius of the circle. And it's kind of like when we do an equation x equals 3. What do we know? X is always 3. Does it matter what y is? No. X is always 3. Well, here's the same situation in polar. What's the radius? Well, the radius is A. Does it matter what the angle is? No, it doesn't. The radius is always going to be A. Now, theta equals theta naught, or theta sub 0, is just a line through the origin. All right, and if we have these ranges, or domains and ranges, if R is only going to be between 1 and 2, and theta is only going to be between 0 and pi over 2, then we have this piece of a donut. That's the area that we're defining by these two things right here. Where's my radius? It's always going to be between 1 and 2, including 1 and 2. Well, where's my angle going to be? Well, it's only going to be between 0 and pi over 2. So it doesn't extend past this to go on around the circle. It doesn't go this way to go negative angles, and the radius in that area that we're defining is always going to be between 1 and 2. So it's all this shaded area. Now, if you were to go and try to define that in parametric or even in Cartesian coordinates, it's going to be a little more difficult. All right, more than one coordinate pair can refer to the same point, and this goes back to the whole reference angles and all that thing. Remember, we can have lots and lots of angles that have the exact same coterminal angle. So we can have 230. We can also have negative 2 if we go all the way around this way. Then we can come back and go all the way around to 210, but then go negative 2, and that gives us the same point. We can also go negative 150 degrees and negative 2, or we can go 2 and 330 degrees. So there are the equations at the bottom. All of the polar coordinates of this point are 2, 30 plus n 360. That becomes the reason that is because of the coterminal angles. Remember, if we go to 30, we can go all the way back around. We have the exact same angle again, the exact same terminal side anyway. And if we have the exact same terminal side, then we have the exact same point with that exact same distance. Now, these are, just understand that you can define these points in a lot of different ways. You're not going to be defining a lot of them in 17,000 different ways or anything like that. All right, and then we have tests for symmetry. There's a lot of symmetry that goes on in polar graphs, and we're going to see quite a few of them when we talk about some of the different types of polar graphs that we're going to run into. But some tests for symmetry. If it has symmetry above the x-axis, says if r theta is on the graph, so is r negative theta. Now keep in mind we're coming from the origin and it's defining that point right there. That's my point. And then r negative theta is defining this point right here. Don't think about these as vectors. They're actually not. They're just defining where the point is. All right, so that's what we're talking about when we have x-axis symmetry. We'll talk about the tests in just a second. And if we have y-axis symmetry, it means that if r theta is on the graph, then so is r pi minus theta. Or negative r negative theta. All right, and then we have origin symmetry, which says if r theta is on the graph, so is negative r theta, or r theta plus pi. And keep in mind, both of these are the same way we were looking at with the previous one. These are the same point. It's just two different ways of defining it. So if these things are true for all r thetas, then you're going to have origin symmetry. Now the symmetry, if you remember, is very much like, it's defined the exact same way. Now notice we're showing this on the coordinate plane, but the coordinate plane actually does not exist. A lot of times we'll draw the polar coordinates on the rectangular coordinate system just because we're used to it. And this gives us a way to actually compare them. All right, and then if a graph has two symmetries, then it has all three. So if you check for two of them, and it has two of them, any two, then it has all three symmetries at the same time. Because remember, all that origin symmetry really means is what? You're reflecting across the x and then reflecting across the y. Well, if it reflects across the x and reflects across the y, then it has origin symmetry. And it's reflected across the x and it's reflected across the y. So it's got all three. Now, this is one of the graphs that are very easy to do, as you can see right here, with polar coordinates, but not so easy to do with rectangular coordinate systems. So we'll look at, in the next video, we'll look at things like this and finding the finding the area that's enclosed by these.